Well, I'm back, you guys, and we're working on 9-6, the root test on this one. So, um, I have the other video out there on ratio, so please take a look at that if you missed the ratio as well. Um, so we can use the root test to see if the series converge. This one will work really well if I have terms of the sequence that have nth powers. Okay, so ratio would also work on that, but for sometimes when everything is raised to an nth power, the stripping off that nth power can be very advantageous. So suppose we have a series um, of a sub n and define then that of our the limit as n goes to infinity of our sequence will take the nth root of the absolute value of the rule of sequence. And we'll watch for what the outcome is. If that value, that limit L, is less than 1, the series will be absolutely convergent. Exactly the same outcome that we saw in the ratio test. If it's greater than 1, we know it's divergent. And if it's equal 1, sorry, it is going to be not much help because it could be divergent, conditionally convergent, or absolutely convergent. So we will just forward this on. So let's look at 1 over 5 to the n. Now, looking at 1 over 5 to the n, you're probably like, well, why? That's a geometric series with r equal to 1/5, and you are correct. We could rewrite this as 1/5 to the n, couldn't we? Which tells us that our absolute value of r, which is equal to 1/5, is definitely less than 1, and therefore it is convergent by the geometric series test. Okay, so I want to show you a simple example though, where using the root test could be a possibility too. So for the root test, we say, well, let's take the limit as n goes to infinity. Let's look far, far down the line of our series as we head to infinity, or as n heads to infinity. And we want 1 over 5 to the n, absolute valued, right? And then we take the nth root of that. Okay, so I just built this exactly like that. Well, this could be the limit. Now it's just about simplifying so that we can come to a terms of what the limit is. And I don't really need the absolute value signs because this is a 1/5, which is positive, raised to a positive number. So that definitely will stay positive. And I could write this 1/5 to the n like that instead of just having my 5 raised to the n. My nth root could be written as 1 over n, in which case it's power to power, and if I multiply my n times my 1 over n, I get 1. So it would appear that this would come out to be a 1/5, which happens to be less than 1, and therefore this would be convergent by the root test because that's the test we utilized. You also could have written this as the nth root of 1/5 to the n, and same conclusion, right? It's just how do you like working with the radicals, or would you rather write with a rational exponent? Your choice. All right, nice and easy one. You know what would happen if I used negative 1/5? Well, then this would be negative in here, but we'd have to retain our absolute values, wouldn't we? And if I then retain my absolute values, my nth would cancel or multiply to 1, and I would get the absolute value of negative 1/5, which would be 1/5 again, and that happens to be less than 1. So it's still convergent, absolutely convergent. Okay, boy, looks like they pick up steam really quick, doesn't it? You can see that the answer to this one is there, but let's work through number 3 on our own. Lots going on, and especially having this big power of n out there, the root test is going to be nice because it's going to just allow us to zap that away immediately. So we've got the nth root of the absolute value of 5n minus 3n cubed over 7n cubed plus 2, all raised to the nth power. Well, we know that the nth root of the nth power will take care of one another, and that gives us then the limit as n goes to infinity of 5n minus 3n cubed over 7n cubed plus 2. I better keep my absolute values on because I have a feeling I could end up with a negative up on top. All right, now analyzing this. If I'm looking at a limit at infinity, I can really zone in on these largest powers, right? Highest degree in the top compared to the highest degree in the bottom. In this case, we get n cubes over n cubes. If that's the case, then it is the coefficients that we want to compare. So indeed, this limit is going to be a negative 3/7, but don't forget we have absolute values on this, and that will equal 3/7. And the comparison then says, well, 3/7 is less than 1, and we are therefore convergent by the good old root test. This test is probably a little bit easier than ratio, don't you think? Just doing the math on it makes it a little bit nicer. This next one we have 2n going on. Let's see if that has any implications to utilizing the root test. It probably is going to be just fine, huh? I think I'll just get rid of this portion and then we'll work below here. All right, let's get it started. The limit as n goes to infinity of the nth root of 5n minus 3n cubed over 7n cubed plus 2, absolute valued, raised to the 2n. And in this case, I'm going to let my absolute values act as a grouping symbol as well, right? Nothing wrong with that. Maybe it would be an advantage to rewriting this, and rather than using a radical, I'm going to demonstrate this one using the rational exponent. Okay, so we've got it raised to the 2n, and then we take this whole thing and raise it to the 1 over n in place of the radical. So when we have a power raised to a power like 3 to the 4th squared, we know that turns out to be 3 to the 8th because we multiply those powers. Well, we'll do the same thing in this case because the rules apply the same. I take 2n and multiply it by 1 over n. You're right, that gives me a 2, doesn't it? So this here is going to simplify. Let's write it this way. The n over the n is going to simplify to just a squaring. Very cool. That's going to be nice because that's going to give us the limit as n goes to infinity of 5n minus 3n cubed over 7n cubed plus 2. I really don't need now the absolute values if I'm going to square something, because that will immediately make it positive. So it'll be a positive result. Absolute values still stay positive. Once again, we're zoning in on the fact that this is my largest degree in top. That's my largest degree in bottom. The comparison between the two says that we should explore their coefficients. That will be the limit. So this stuff will get squared, and that'll make this 9/49 positive, which is less than 1. Therefore, oops, weird, therefore we get that this is convergent, absolutely convergent by root test. Okay. That was example 4. On the back side, example 5, let's play this one out. So we will go into the limit as n goes to infinity. The nth root, I've been writing it. Oh, what am I going to do on this one? It's got me confused, you guys. over n. Well, let's just play it out. Absolute value this. And then instead of making the big radical, I think I'm just going to go 1 over n. Would that be okay? The top will be pretty simple, won't it? You know, if I have a power applied to a fraction like we do, we can say, well, it's going to apply to the top. We need some absolute values. Let's put them right in here. Over the bottom, which is already positive, so I'm going to skip my absolute values. Like so. Now, the top, n times 1 over n will make this just simply 1, won't it? And then I'll have the absolute value of negative 12, which will turn out to be 12. So my numerator I see coming out as a 12. If I limit, the limit of 12 is 12. Okay, what about the limit of n to the 1 over n? Well, let's just stop and pause here. That's like saying 1 over infinity, which it's going to be 0. I get n to the 0, which would be 1. If you wanted to replace this n with the idea of largeness, I'd have large raised to the 0, which still will be 1. And we can see here that this is going to be our limit, which happens to be greater than 1. And we will get a conclusion that this series is actually divergent by the root test. Hopefully I explained that step by step for you, that you could see how I came up with my results on that. I really applied this power to each the top and the bottom, which is definitely allowed. If I had 3/5 to the second, if you ever are in doubt, guys, just write a simpler problem and come back to something that you know extremely well. And yeah, I know I can do that. Right? Otherwise, I can say this is 3/5 times 3/5, and I get the same answer as I did when I broke up my squaring to each individually, top and bottom. All right, always use that. Go back to something you know to find out something that you may be questioning. All right, and that leads us into example 6, doesn't it? Well, let's get it started. The limit as n goes to infinity of n to the nth over 3, 1 plus 2n. This will be the root test. So absolute value, I'm going to do these separately. And then I'm going to apply my 1 to the n and 1 to the n top and bottom, so that I don't have to take this extra step like I did above. Not that it's wrong. It's just I'm saving just a little bit of paper, I guess. On top, that's going to turn out to be just n. I don't need absolute values because n is always positive. On the bottom, I'm going to get 3. If I multiply my 1 over n inside, I'm going to get 3 to the 1 over n plus 2n times 1 over n will give me just a 2. Will that be positive? Indeed. So we can let our absolute value signs drift away because we did consider it, and it's not necessary to have them. Would this be the same as saying 3 to the 1 over n times 3 to the second? Well, if you aren't sure, go back to something you know. Is this like saying 3 to the n, or 3 to the 2 plus 1 is 3 to the second, 3 to the first? Well, this would be 9 times 3 makes 27. And this would look like 3 to the third, which is also 27. It appears like that's a good rule to use, right? If I have exponents that were added, then it meant that the bases were the same, and that's what leads us into addition of exponents. How does that helpful? Well, I get a 9 here, don't I? And I could pull my 1/9 way out front because it does not have an n in it. And this will be, so I'll have 1/9, and I'd have infinity here, and 3 to the 1 over infinity. Well, that's like saying 1/9 times something large over 3 to the 0. Well, that's going to be like a 1, isn't it? Because this would be going to 0. All right, so we end up with 1/9 of infinity. Gosh, how large is that? Pretty darn large. So that would end up being infinity, which is greater than 1, and therefore divergent. Well, I guess there's one more to do, and I might as well do it. These will actually roll along pretty quickly, don't they? The limit. Ooh, what's happening, guys? The limit as n, not sure. Let me just click that off. N goes to infinity. I see nth powers, and anytime I have powers, I think the nth root test is a great test to use. I'm going back to this notation, just kind of changing it up. You find what's comfortable for you. I guess that's the main idea. And, I think what I want to do is look at the numerator and the denominator separately, and I am clear to go on that because we have rules of the rational exponents that allow us to do this. And we could have these absolute values out here if we wanted to. Well, this first one, you may say, you know what, I don't like looking at radicals, so I'm going to get this changed up immediately and rewrite it as a power, and that is perfectly fine. Kind of with you on that one. All right, so the top analysis, n times 1 over n, simply a 1. I'm coming out with an n on top. I better write limit out here. Limit as n goes to infinity. And absolute value of n is n. All right, bottom, distribute. That's going to give me a 3 to the 1 over n. We talked about this last time. A 3 to the 2. If we allow this to go to infinity, what did I do wrong? I feel like I did something wrong, guys. No. I'm sorry, did I do 2? I did the same problem twice. Okay, I thought I was doing a different problem. I'm sorry to waste your time. This is the same as the result of the last time. It goes to infinity. This is the one I wanted to do. All right. Sorry to waste time. Let's get this last one done. N goes to infinity. We have n over 4 to the n, and we're going to nth root this. So nth root test, absolute valued. If you don't like it that way, let's break it up. And I'm going to have n to the 1 over n, absolute valued, over 4n to the 1 over n, absolute valued. That's like having n to the 1 over n. That's like saying n to the 0, isn't it? If I let this go to infinity, I'm going to have n to the 0 or infinity to the 0, which is 1. And then n times 1 over n will simply be 4. And we get a 1/4 limit. Woo-woo. That's less than 1. Therefore, we are absolutely convergent by the root test. Awesome. That gets you all the examples in under 20 minutes. Yippee. These are the problems I'd like you to practice. And the root test goes a little bit quicker, so I know there's a bunch there, but I think they will go fairly quick for you. So good luck on that. You know what? I see I did that one for you, so you can go ahead and cross that one off, huh? That was our last example, number 7. All right. Hey, hang in there. See you later.